Okay, ladies and gentlemen, we had another great week, and so I want to make sure we come back and do all the problems that we did this week. Again, titles or topics of the problems here are straight up just potentials. Then we jumped into the link between potentials and electric fields, and then we did some problems on capacitance. And so those are the problems that I want to do today. I want to blast through them to make sure that we're all on the same page. We'll give you the answers, and then we will go from there. So let's jump right to it. Okay, first two problems are listed here. We see the first one says some nanocoulomb charge at x equals 0, and another one is at x equals 4. Let's get a sketch of this. We got a Q1 here and a Q2 here. They then ask at what point or points on the x-axis is the electric potential 0 based on those Q2s. Well, in order for us to do this, let's make sure that we get all of our distances right. Why is that? Because we know that what we're going to be asking for is that if we have a point on the x-axis where the potential is 0, then what are we really saying? That V net there would be equal to V1 plus V2. And each one of those V's is going to be its KQ1 over R1 plus KQ2 over R2, right? Where, again, the R1 by definition is the distance from charge 1 to the point that we're looking at. Same thing with R2, distance from charge 2 to the point that we're looking at. Okay, one of these charges is positive, one of these charges is negative. The stronger charge is the positive charge, which means there's going to be only two possibilities where this thing could have a 0 potential. I'll do it as 2 points, one in purple and one in red, and then let's draw all the line segments that go along with it. I'm just going to pick this up and move it down a little bit so that we have a little bit more space for the line segments. So if we imagine the first point somewhere that we don't know where it is, but let's call it at a point X in purple, and the other point we'll do a little bit later over here in red, okay? Well, again, by definition, let's draw the line segments. The distance from the first point from the first charge to that point, well, that's just the unknown distance x. That's what we want to solve for, okay? The distance from charge 2 to that point x is this line segment in green, and we know the distance between Q1 and Q2 is 4 centimeters, which means that we can figure out the distance between Q2 and x by just using black segment minus purple segment, which means that this one is nothing more than 4 minus x. When we come down here then, we see that what we're saying is V1 is K Q1 over x plus K Q2 over 4 minus x, and that whole thing has got to be equal to 0. Once again, I remind you that when we plug in charges for potentials, we plug in the charge with the sign. So if it's negative, you plug in negative, positive, etc. Right? But what we're solving for here is x. We have an x on both sides, and it sucks. It's in the denominator. No problem. Let's move. Oops. Let's move this whole term to the other side by subtracting it, so that we get a k q1 over x is equal to a k q2 4 minus x. Now, upon doing this, how are we going to get the x's upstairs? We're going to cross multiply. But before we do that, we have a k on both sides so we can cancel out the k's. This leaves us with a 4q1 minus xq1, that's distributing out the left-hand side, is equal to q2 times x. We have x's on both sides of the equation, so we got to bring all of the x's together. So I'm going to add xq1 to both sides. We see that 4q1 is equal to q2 plus q1 in parentheses x, because I factored out the x when I brought the xq1 over to the other side. Okay, now just last thing to do before solving for x, we see that x is nothing more than 4q1 divided by q1 plus q2, and that equation now is very simple because q1 is just 3 nanocoulombs, q2 is negative 1. Okay, so we plug those in, boop, 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 bop, bop, boop. Oh, I'm sorry, I'm lying to you. When I move this over, it should have been subtracted, which meant this whole time this should have been a negative, which makes this guy a negative, which makes this guy down here, I totally apologize, a negative. But you can catch me on that one, right? Which means that, again, Q1 minus Q2 should be 3 minus minus 1, which is 4 nanocoulombs, which is 4 divided by 4. Q1 nanocoulombs divided by nanocoulombs. This leaves X as just being 3 centimeters, okay? How do we get that other point, right? Because that was one answer, there's another point out there in red. We just have to do the exact same procedure, but redraw the line segments because the unknown distance X is not that purple line anymore. That unknown distance X is now out here, right? Which means that this would be R1 for the second part of the problem. And again, how do we get the new green line segment, namely, oops, I don't want to put that there, namely from charge 2 to that unknown point? Well, now this would be X minus 4 instead of 4 minus X, which means the new equation that we're solving is KQ1 over X plus KQ2 over X minus 4 is equal to 0. Almost the exact same equation, it's just off by a negative sign. And you can see already how that negative sign is going to trickle down. I leave that algebra to you for practice, which I highly recommend that you do. And we see there that X would mean nothing more than 6 centimeters. And we have it, okay? That was all for that first problem. Now we have this problem with 3 charges configured into a triangle. We've seen lots of problems like this before where we have charges and we look at the net potential at either the net field or net force or net whatever at a particular point. And this is one of the annoying ones where we have 3 instead of just 1 or 2. So if that is the case, then let's make sure that we're all on the same page as to how we get this. Nice thing about this, it's an equilateral triangle. So I'm going to draw on this a bit. Coming up here, okay? First thing that we can see is that if we call this charge 1, we call this charge 2, and we call this charge 3, right? We know that V net, just like how we had before, is going to be V1 plus V2 plus V3, right? At the middle point, we get contributions from each of those charges. And we know how each one of those formulas is going to look. KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. So if we knew R1, R2, and R3, we're done because we have Q1, Q2, and Q3. Okay, so R's are the relative distances between the charge and the point itself. So let's dive in. Equilateral triangle, so I hope that everybody believes me when I say that R1 is going to be the same as R2 is going to be the same as R3, so just call it R. If I find one of them, I have all of them. So which one's the easiest one to find? For me, it's the one on the bottom left, right? This is the R that we're actually talking about here, yes? Right, the distance from the charge to the, right, that would technically be R2, but we said R2 is the same as R, right? Okay, and now what else do we know? We know that this line down here is 3 centimeters. So let's just drop a perpendicular, shall we? If we drop a perpendicular, then we see that this segment that I'm underlining now in green, right, is half of 3 centimeters or 1.5 centimeters. The nice thing about that is that in an equilateral triangle, we know the net angle is 60, and if this line bisects that 60 to get straight through to the center of the equilateral triangle, it means that this angle is 30. So if we have an angle and we have the adjacent side, that's enough to get the hypotenuse by SOHCAHTOA, in particular the K in SOHCAHTOA. Cosine is adjacent over hypotenuse. So again, why don't I just pick up this triangle? Okay, why don't I just pick up this triangle and paste it down here. Oh gosh, that's not what I want to do. I lied to you. I am not going to do that. I'm just going to redraw this triangle. Okay. This is 1.5 on the side. This is 30, and this is the unknown R. So we know then by definition of the cosine of the angle then, which here the angle is 30, we know that by definition the cosine of 30 is the adjacent 1.5 over the hypotenuse R, and that we can solve for R. Once we solve this for R, we get R is going to be 1.5 divided by the cosine of 30, which is a number that's about 1.7. Once we have this value for R, that's the same for R1, R2, et cetera, and we can plug that into this formula back up here. And upon doing so, if they each have the same denominator, and one charge is Q2 and the other ones are each minus one of them, then we see that, well, if R1 is the same as R2 as R3, then this really becomes K over R, Q1 plus Q2 plus Q3. And I remind you that we're plugging in the actual charges with their signs We can't ask for anything better, ladies and gentlemen. We get a whopping 0 for the answer. Cool. On to the next day. This was our link between potentials and electric fields, right? And so this is us talking about the concept about really using this formula, right? And to be fair, right, it's the potential difference is equal to E times D, where again, I remind you that E is the constant electric field generated by you having a potential difference. And D is the separation distance, not between any arbitrary points, but it's the separation distance between the two surfaces of equipotential. That's going to become important in each one of these to make sure that we don't double count or over count for anything in particular. And again, we solved some other problems like this in a previous video, so hopefully it should be no problem. So what are the other two rules that we have to exploit? Electric field is always perpendicular to the equal field lines, and it always points in the direction of decreasing potential. If that's the case, then check it out. The first problem, they give us the electric field and the separation distances. We want to go back and find the potential. So again, since the potential is, I'm going to mark this up, since the potential is drawn going exactly to the right, and we know that it has to be perpendicular to lines of equal potential, the only way that it can be perpendicular is if this is one of the lines of equal potential and this is one of the lines of equal potential. There could be, not that one, there could be other lines as well of equal potential, but the two that we care about are these ones, A and B. And what do we know about these lines of equal potential? Everywhere along that line, the potential at A is the same there, as there, as there, as there, and here, everywhere along that line, the potential is the same. Once we see it like this, they tried to be misleading in this problem, right? They wanted you to think that you need the separation distance as being the hypotenuse, but you don't. You need the separation distance, remember, by definition, is the distance between the equipotential surfaces, which we now see that distance is nothing more than this distance, which is already given as 7 centimeters. So we have an electric field, we have the separation distance, therefore we can use this to find delta V is E times D, which is going to be our 7 centimeters, bad unit, 0.07 meters, times our 1,000 volts per meter, and then we have this come out to be nothing more than 70 volts. Cool. When we can't find potential A or potential B individually, all we can find is the change in potential. But they do ask us which one has a higher potential. Again, that's rule number 2, right? That the potential at A, I'm sorry, the electric field flows in the direction of decreasing potential. The arrows are pointing to the right, so that tells us that whatever they are, potential A has got to be bigger than potential B since the electric field is flowing that way. The next problem is basically the exact opposite of this, where they give us now the equal potential lines and we have to pencil in the field. So let's do that. Here's our equal potential lines. We know that we first draw a line that is perpendicular to them. There it is. And we put the arrow facing in the direction of decreasing voltage. 200 is less than 0. Boom, we come right here. That is our electric field direction. We can figure out the magnitude by, once again, we know the fact that delta V is equal to E times D. We know delta V, we know D, so E then is nothing more than our 200 volts divided by, again, 0.01 meters. We have to convert that to meters, and this is going to be 20,000 volts per meter. That is the magnitude of that field. The direction is already shown on the figure, and that's why this angle of 45 degrees comes in here, because if we zoom in and put this on the coordinate plane, then we see that that angle of 45 has to be right there. And if that angle is 45, then our typical measurement of angle starts from 0 and goes clockwise, which would be a 180 plus 45, which is an angle of 225 degrees. Last but not least, onto the topics of capacitance, right? When we studied capacitance in the previous video, we said that there was 2 pieces that we wanted to highlight. One is the actual definition of what it means to be capacitance and a capacitor. I remind you that capacitance is just, you can have one, I can have one, anybody can have one, right? It's just defined as an object's ratio of its charge to its potential. It's object's ratio from its charge to its potential. Then the second one we said was that we can mess around with that if we know the dimensions of these parallel plates inside the capacitors, right? And show that it is actually a material property, which is equal to epsilon naught A over D. And last but not least, we said that, well, we can shove other things in between the parallel plates of capacitors. And in doing so, we can change the overall capacitance, namely change the overall ratio of Q to V. Let's do it. The first one, an uncharged capacitor is connected to the terminals of a 3-volt battery and 6 microcoulomb flows to the positive plate. There it is. You have the capacitance. The charge, 6 microcoulombs divided by the voltage, 3. Ratio, 6 to 3, a ratio of 2 in some unit set, right? That's the best that capacitor can do. Pause. You take that battery off, you replace it with a 5-volt battery with the positive and negative terminals connected in the same manner. How much more charge flows to the positive plate? You haven't changed the capacitor, right? You haven't changed the capacitor at all. So whatever the capacitor could do before, it can only do that much again, right? Its charge to voltage ratio could only be 2. 6 to 3 before now has to be X, or I'm sorry, has to be 5. Has to be X to 5. If that ratio has got to be 2, we already know the answer has to be 10 then, because that ratio of charge to voltage has to be preserved. Let's do the work to make sure that we get there, yes? So if we do this, we know then by definition, the capacitance is charge over potential difference, okay? And so in the first instance, right, if you will, the amount that you charge, the capacitance Q1 is equal to the charge Q1 that you put on it with its respective V1. Then we pop that battery off, right? And we say, well, now we go to C2, which is Q2 divided by V2, but then we realize that we haven't changed the capacitor. We haven't changed the dimensions of this. We haven't put a dielectric in it, right? So C1 has got to be the same as C2, right? It's just C. It's just still the same capacitor. So that tells us that if this is C1 and this is C2, then Q1 over V1 is Q2 over V2, which is exactly what I said a minute ago before we wrote any math down, right? That the ratio, 6 to 3, has got to be the same as blank to 5. Let's solve it then for what we want. Solve it for the unknown Q2. And when we solve this for the unknown Q2, we see that Q2 is going to be V2 to V1 times Q1, which is going to give us 10 microcoulombs. Again, does that check out? Yeah, the ratio 10 to 5 is still 2, just like 6 to 3 was 2. Technically speaking, in this problem, though, they ask us how much more charge was there in this instance, right? So here we just solved for what the second charge was in this instant, right? 10 microcoulombs. So therefore, how much charge difference did we have? We started from 6, we went to 10. Technically speaking, then we have an overall net charge of 4 microcoulombs. Okay. Last but not least, the second one demonstrates the second piece that we were talking about a couple of minutes ago, which is what about if you know the dimensions of the parallel plates and we shove a dielectric in there, okay? So if that's the case, the first thing that we need to realize is that the way that we go from being a regular capacitor to something with a dielectric is that the new capacitance C is just the dielectric constant times C0, where the dielectric constant K is something that you can look up in your textbook or online because they tell you here that it's aluminum. So K is a given here. C0 would be the original capacitance as though there was just air in between the parallel plates, right? Like always, that's going to be charge divided by voltage, or if, like we said at the onset of this, if we know the material properties, this is going to be our epsilon naught A over D from the last video. Well, guess what? Here we know epsilon naught, it's a constant of nature. We know the area because if it's 35 by 35, well, then the area is just 35 by 35. Centimeters is bad unit, convert that to units. And we know if there's a 0.25 millimeters thick sheet of paper in between, that is the separation distance, right? If it's just wedged exactly in between. So we also know D. So we're done. This is basically now a plug and chug. The net capacitance with the dielectric constant K then is just epsilon naught A over D, which by the way, if there was no aluminum foil there, if there was just air in between, the dielectric constant would be 1, and we'd be back to the formula that we know and love. C is epsilon naught A over D. This is a straight plug and chug. We plug these numbers in, and I get a number of 13 nanofarads. Okay, ladies and gentlemen, I hope that you see that these problems, there is something that I really, really want to stress, right? The first two problems that had point charges where we're figuring out things between them, right? That is the big part of the story that we've been telling for like 2.5 weeks now, right? That if you look at it from the certain perspective, you're saying, how many contributions do we have at some place? You add up the different contributions and that gives you the net. You plug in the proper formulas. You make sure that you go slow with geometry, right? And if you were doing force and field, which we did not do today, but if you were doing force and field, like the previous videos, you would need to keep track of your vector directions, x's with x's, y's with y's. If you're doing potential or potential energy like we did this video and the last video, then we don't care about direction. We can just use this as a scalar and we solve the problems like we did there. The second piece of this, not difficult algebraically, not difficult mathematically. This is the piece that's a bit more difficult conceptually, right? This is now the physical application that when you have a potential difference, the result is an electric field. That delta V gives us an electric field that is proportional to the separation distance between these two lines of equal potential, and that's where we get the formula delta V is equal to ED. Nothing difficult about there, but if we don't know what distance we're talking about or what the electric field looks like or how we draw it, then that formula is going nowhere. Second piece again, that is nothing more. I know we get hung up on the word capacitor and capacitance. We're thinking about electronics already. We're not there yet, right? Right now, capacitance is nothing more than just a flavor. It's a name that we give to a ratio because it's a common ratio, right? If James has a red shirt and blue jeans, right? Well, I can define something called, I don't know, James's style, right? Which is a ratio of his shirt to his jeans, right? It's just another thing that we can quantify about me already knowing about shirt and jeans. Same thing goes where capacitance is just a property that we just define as charge to voltage. Okay, so hopefully that gives you a good conceptual overview to match these problems. This will become important as we move forward into the next topics, which is going to be about building simple circuits. So that's when we'll talk more about the component nature of these. And I don't mean components like vectors, I mean like little electronic components, okay? But we'll get there. But for now, with these problems and the ones that we did in the videos, all these match the stuff that we're going to be doing both in class and in homework. So just keep it up, stick with it, and I hope you have a great night.